Okay, establish the identity tangent x over secant x minus 1 minus secant x plus 1 over tangent x is 0. Okay, we've got a couple options here. Two things come to mind that we've done a lot. Change everything to sine and cosine, which I could do. Or I also have two fractions I have to subtract. I could also do that by finding LCD. So I'm going to start there because I do, instead of change everything to sine and cosine, I'm tempted to do that. But I do know there's a relationship between tangent squared and secant squared. So that might show up in this one. So I'm going to go ahead and do the trick that we like to do. Sorry, try that again. That was way off. Add these two guys together. So I need a common denominator. So it's going to be the product of these two denominators, right? So that means I need a tangent x here and a secant x minus 1 here. Now I have a common denominator, but if I put this in the denominator, I have to multiply the numerator by that. Excuse me. And if I put this in this denominator, then I have to put it in the numerator or multiply the numerator as well. So that gives me tangent squared x minus, multiply these two together, those are conjugates, secant squared x minus 1. That's the F and the L in FOIL. And in the bottom, I just have my LCD. Okay, so that's good because now I know that I have an identity. You go to my identity sheet, and this one's going to actually work out pretty nicely, I think, because secant squared minus 1, I know, is equal to tangent squared. All right, and once I do that, now I have tangent squared x minus tangent squared x. I don't really care what's in the bottom. There's my LCD because that minus that is 0, so I end up with 0. Okay, so that covers a couple things we see a lot in identities. We ended up with a Pythagorean identity. We did the thing where we get common denominator, add two fractions together. We had a couple other things that we did when we did those, a couple other methods, factoring, change everything to sine and cosine. If you were to change everything to sine and cosine, I think that one would work out as well. You just end up with different Pythagorean identities. Sine squared plus cosine squared equals 1 or some version of that. Okay, moving on. Oh, good. Let's do some easy ones. Polar coordinates. So if I asked you to do polar, so these three things kind of go together. These were all in the same chapter. Polar coordinates, complex numbers, and vectors, because they had both the xy form and the polar form or the trig form. So I could ask you to convert polar to rectangular. I could say 5, 2 pi over 3, right? That would be, go out 5, rotate 2 pi over 3, and you're right here. What's that xy coordinate? Well, this is 5, this is 2 pi over 3. This right here is a 60 degree angle, pi over 3. So you have that relationship. Remember, the relationship save you a lot of work if you can use your relationship between the two sides and a 30, 60, 90 triangle. Or you could even do this the easy way. X equals r cosine theta. This would be even easier to use these formulas. All right, so basically it's just 5 times the cosine of the angle will give you the x value, and 5 times the sine of the angle will give you the y value, right? So this would just be equal to cosine of 2 pi over 3. Cosine of 60 degrees is a half, so that should be negative 1/2 because we're in quadrant 2. So 5 times negative 1/2 or negative 5/2. And then this would be 5. The sine of 60 degrees is root 3 over 2, and it's positive. So there's your y value. Here's your x value. So to put that in a point, you end up with that xy system. Also be able to go from this way back to polar form. Okay, and you can just draw your picture like I did, figure out the sides, or you can use these formulas. Complex numbers. Let's say give you a complex number like z1 equals 3 minus 3i, and z2 equals let's say just 6. All right, so those are two complex numbers. Know how to do the following. Know how to multiply these two guys together. Know how to divide them. Let's make this -6. Know how to divide them. That would be, we could go z1 divided by z2. And know how to raise them to powers, z1 to the third. Okay, so for any of these three examples, I would have to put them in complex form, right? So z1 would be back 3, down 3. Back 3, down 3 right here. There's your angle. That should be 5 pi over 4. And the radius, or the magnitude of this complex number, or the modulus, I guess I should be saying, is 3 root 2, right? Because it's a 45, 45, 90 triangle. So here's your complex form. And we said we're at 5 pi over 4. Sorry, a little messy. 3 root 2 cosine 5 pi over 4 plus I sine 5 pi over 4. This one looks a little interesting. Z is -6. That's right here. No, that's in the x direction. Sorry, -6 should be right here. Okay, there's no I component, so I don't go up or down. And that's 180 degrees, right? So this is equal to 6 cosine 180 plus I sine 180. All right. Or since I did cosine pi plus I sine pi in radians. Okay, so remember how to, let's just do one of them. If I multiply, the formula I have is to add the two angles and to actually do the multiplication of these two numbers. So 3 root 2 times 6 is 18 root 2. And then the angle would just be 5 pi over 4 plus pi, or 4 pi over 4, 9 pi over 4. Plus I sine, same thing goes in there. Okay, so to do this one, you subtract the angles. To do this one, you multiply the angle by 3. And then the operation on the R value is the same, division or raising to power. Okay, sticking with that, we had two forms of vectors, which is why they fell into the same category. So let me actually give myself enough room this time for vectors. I can give you a vector in this form. Right, like, let's say, sticking with special angles if we want, we'll go -1 root 3. Okay, that's a vector in XY configuration. This vector in polar form is pretty similar to what we just did. We have to figure out the magnitude of the vector, right? So it'd be the magnitude of the vector. And then we can multiply it by the unit vector, cosine of the angle in the I direction, plus the sine of the angle in the J direction. Very similar. Different notation, but very similar. So if I go back 1 up root 3, the magnitude there should be 2. Or you can do Pythagorean theorem to get there. And then this, because I gave you a special angle, that's a 60-degree angle. That's the same angle. We saw that a little bit earlier. That's 2 pi over 3, right? Because this is pi over 3 reference angle. So it would be the cosine of 2 pi over 3 in the I direction plus the sine of the same thing, of course, in the j direction. Okay, this is very similar to what we did for polar and for complex numbers. Two forms, x, y, polar, or trig. And then we did operations on vectors. So if I also gave you a w, let's just call w5, 6, I can ask you for stuff like this, 2v plus 3w, right? And that would just be 2 times v plus 3 times w. Right, that's just everything there staying in xy form. So we just distribute that and go from there. So it'd be negative 2 root 3 plus 15, 18. And then we can add these together. Negative 2 and 15 is 13. And then I can't really do much with this when I add them. 18 plus 2 root 3 would be how I write that. What else? Let's do a unit vector real quick before we move on to some more algebra stuff. Unit vector. So let's say I said unit vector in the same direction as, let's do w. Unit vector for w. So remember, you got to find the magnitude of w. 25 plus 36 is 61. That's the magnitude. And then, so the unit vector, we would just divide each component by its length. So 5 over root 61, 6 over root 61. Okay, I better stop this video here before it gets too long to upload. This is part 2. One more part left, I think. Part 3 coming up next.